Today I will be presenting the data and analysis collected by the voltage generation station. I'm Joshua Rogers. My other teammates include Jason, Kevin, and Joshua Solomon. Today during this presentation I will be going over the system overview, the steady state operating curve, the results of the steady state and step response experiments and models, the results of the sinusoidal input methods, the results of the relay input methods, comparison of data, and summary and conclusions. As you can see, this is the block diagram for our system. We have an input that's in percentage, our voltage system, and our voltage output in volts. This is the schematic of our voltage station. We have the action element, the voltage transmitter, and the voltage controller. All goes into the system to turn the lights on. This is an example of one of our graphs over time. Input up to has a transient period here in the blue section. The red section shows the steady state output, which is 90 volts in this graph. This is a compilation of the data shown on the previous screen to create our steady state operating curve. As you know before, we had problems in this area here. We have now fixed this point on our graph, and the average slope for our steady state operating system is 1.5. This graph shows an example of our step response. Steps up from 85% input to 88% input. And this shows how the output increases with the step response. You'll notice this point right here. You can see a slight oscillation here. That is not typical of a first order response, which would indicate that our system is not first order. This is the model results for our step response. You can see we have the purple line here to try to match our experimental data in the red. And these were the equations used to model the step response. And our parameters, we have PD of 10 seconds, amplitude of 3, K of 1 volt per percent, a T0 of 0.03 seconds, tau of 0.1 seconds, baseline input of 85%, and a baseline output of 85.2 volts. This bar graph indicates our gains of K for the step response. You can see they are fairly similar. The K for the down step is slightly less than K for the up step for each range. This bar graph shows our dead time for our step response. You can see every section except for the 93 to 97%, the dead time for the step down was larger than the step up. And it shows the time constant for our step response data. From our step response graphs, we have determined the parameters. Steady state gain for a step up is K of 0.8 volts per percent, a dead time of 0.025 seconds, and a time constant of 0.05 seconds. For a step down, our K was found to be 0.75 volts per percent, dead time of 0.03 seconds, and a tau of 0.05 seconds. As you can tell from the two, the results are nearly the same. This block diagram shows what we have been doing the past 2 weeks, taking our inputs of sinusoidal functions and a relay response, moving them into the first order plus dead time parameters, and reaching an output of volts. This is an example of our sign response graph. You can see we have a base input of 90.5 volts for this example. It increases up to 92 and decreases down to 89%. And it oscillates up and down between those values. Our red line indicates the output, which is also oscillating. You can see here the period below about 6.25 seconds is transient period. We don't consider that data in our analysis. Everything beyond that is steady state. We were looking at the amplitude ratio between the input value and the output, as from about 90.5 up to 92 compared to the output, which is about 87 to 85 volts. We also looked at the phase shift between the input and the output, as indicated right here. At different frequencies, we were able to find different amplitude ratios and plotted them on a Bode plot, logarithmic axes on both the y and x axis. And we also plotted the phase angle versus the frequency. The frequency is in logarithmic axis. And from here, we could take a model and try to fit our experimental data. This is the Bode model of the amplitude ratio versus the frequency. For this model, we were trying to get our K value to correspond with our low frequency amplitude ratio. And for that, our K for this set of data turned out to be 1.65 volts per percent. And we were also trying to get the tau value to correspond with the corner of this data right here. And so tau ended up being 0.12 seconds for this set of data. We also modeled a graph against the phase angle versus frequency chart. For this model, we were trying to match up the model graph with the data at the ultimate frequency of negative 180 degrees. You can see that's about right there, which corresponds with a dead time of 0.03 seconds. This is the data collected for our sign response graphs and models. You see our gains for 1.6 volts per percent, 1.5 volts per percent. Our orders are definitely not first order. Ultimate frequency is also similar, 9 cycles per second, 8 cycles per second. KCU is 1.0 and 1.2. Tau is 0.011 and 0.08 seconds. And dead time is 1.8 seconds and 3.8 seconds. And from the Bode plots, we were able to determine parameters for our sign response graphs of 1.65 volts per percent and 1.40 volts per percent, 0.13 seconds and 0.03 seconds for tau, and 0.03 seconds and 0.05 seconds for dead time.
After analyzing our system with a sign input, we analyzed it with a relay response. For those not familiar with a relay response input, it has a floor value shown in here in this graph is 92 amperes, and a ceiling value of 96%. And there's a set point with an output of 94 volts, and it rises to the ceiling value until the output exceeds the set point. At that point, the input then drops to the floor value input until the output drops below the set point. This happens periodically until your experiment time runs out. This is just an example with a floor of 92, a ceiling of 96, a set point of 94. The transient part is from 0 to about 5 seconds, and Everything else is basically steady state in the sense of it's what we're looking for. I concentrated in the area of 20 to 21 seconds for my analysis. Okay, so what I was looking for the relay part is the change of the delta M in input change, the period between the peaks, and delta C, the change in the output from peak to peak, and then this B constant for the difference. Just time between the peak time and 1/2 of 0.75 of the delta C value. These are the results of my relay and Kevin's relay system. My values were in the 92 to 96 range, floor of 92 and ceiling of 96. Kevin's was the 96 to 100 range. His set point was a 98. You look here, the values are almost similarly. The ratio between delta C and delta M is 1.3, the uncertainty of 0.1. His was 1, and the uncertainty of 0.01. The frequency for this one is 77.3 hertz, the uncertainty of 0.6. His was 7.1, the uncertainty of 0.1. So far, they're very similar. The KCU value is 1 with an uncertainty of 0.047. His was 1.22 with an uncertainty of 0.01. These are the parameters that we developed to find tau, T0, and K. So far, they're very similar, 103, 103. Uncertainty is very low here. The F is 0.74, his is 0.72. C is 0.64, his C is 0.54. Uncertainty value is still low at this time. This is the omega, 46. His is 44, 46.18, 44.35. This uncertainty is large due to this value being typically large. The tau, TO, and K values, parameters that we're going to analyze between the relay and the sine, these came up to be 0.084 seconds. His is 0.084 seconds also. The uncertainty is 0.026. His is 0.02. The T0 is 0.041 seconds. His is 0.042 seconds. Again, the uncertainty is very low in here. K value is 1.96. Uncertainty of 0.5. His happened to be 2.952. The uncertainty of 0.54, which is possible that we might need to go back and check that out some more. But for the time being, that's what we have to work with. Now this is a comparison of the data between the sine and the relays developed by Josh, both Josh's and me and Kevin. On the outside, we have the sine response due to Josh. The inside is sine response due to Josh Solomon. The two inside is the relays. The KCU values, they're all relatively similar. Slight variation between those. The K values, they're basically the same thing as well. This is Kevin's K value that came up with. He's a little out of range. The tau values, very, very similar, very low. And T0, same thing. They're very, very small, but yet they resemble about the same value. And then the two ultimate frequency values for the sine. Josh Rogers was 9, and Josh Solomon was 8. So they're about the same there. In conclusion, we believe that that the sine response parameters and the relay response parameters are basically identical. There are slight variations in the uncertainty values. That some parameters of the sine values fall out of range. This could be due to not enough data points collected for a lab view. I know there was about 6 points that created 180 degrees of my relay system, and that could be not efficient enough to get accurate values for some of those parameters that we were using. And basically we're concluding that the parameters found in the Bodie monoplot will be used for